Section 9.8 is power series. Now we can represent a function as an infinite series. For example, we can represent e to the x as the infinite series 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus all the way down to that x to the n over n factorial. So what we're going to look at in this section is the definition of a power series, and then the interval of convergence of a power series, which is the same as the domain of that function. What x's can you actually plug into that power series for that power series to converge? And we're going to finish the section off by looking at how to integrate and find the derivative of a power series. Let's start off by defining a power series. Now, a power series is a series in this form: the sum from n equals 0 to infinity of a sub n times x to the n, where x is a variable, and that expands out as a naught plus a sub 1 times x plus a sub 2 times x squared, etc. And this is a power series centered at 0. More generally, if you have a power series that's centered at x equals c, that's going to look like the sum from n equals 0 to infinity of a sub n times x minus c to the n. So the only difference between these two is this is just an x because you're centered at 0, and here it's an x minus c because if you were to solve this equation, you have x equals c and you're centered at x equals c. But it expands out the same: a naught plus a sub 1 times x minus c plus a sub 2 times x minus c squared, etc., all the way down to a sub n times x minus c to the n. Now for each one of these, this guy right here, this a sub n, this is just the formula that you're multiplying your powers of x by. Now what we're going to do first again is find the domain of the series, and remember, domain just means what x's can you actually plug into your function. Since we have our function here as a power series, what we're concerned with is what x's can we plug into our power series for that power series to converge. How do we do that? We look at this theorem, convergence of a power series. So the theorem convergence of a power series says the following: for a power series that's centered at x equals c with a radius of convergence r, exactly one of the following is true. So we're going to look at the three possibilities first, and then we're going to talk about how to determine which possibility we are. So your three possibilities are these. The first one is that your series only converges at its center. The domain of that series is then just going to be c, and its radius of convergence is going to be 0. Now note, every single power series converges at its center, and the reason for that is, if you think about it, if you're centered at x equals c, and then you're plugging in a c here for every single one of these x's, then every single one of those terms is just going to be c minus c, which is 0. So then this converges because you're just adding 0 plus 0 plus 0 plus 0 plus 0, and that's why it will converge. But the first option, again, for a power series is that the only thing that's allowed in its domain is c, or that it only converges at its center. The second option is that your power series converges for all x, so its domain would be negative infinity to positive infinity, and that radius of convergence is equal to infinity. The third option, and the one that happens the most, is that the series converges absolutely for the absolute value of x minus c less than r, and it diverges for everything else, and its domain is this thing, c minus r, comma, c plus r, where r is its radius of convergence. So I put it here on a number line to try to make it where it's visually understandable. Basically, you see here that you're centered at x equals c. So if I'm centered at c and my radius of convergence is r, that means that I can move r units away from c. So if I'm moving r units to the left, this endpoint happens at c minus r, and if I'm moving r units to the right, this endpoint here happens at c plus r. So it's possible that your series just converges for a set of numbers between c minus r and c plus r. Now for option number 3, please note that we are going to have to check the endpoints to determine if they should be included or excluded from the domain. So we're going to have to figure out, okay, when we're this number, should that number have a parentheses, which means it's excluded, or should it have a bracket, which means it's included? Same thing for whatever that number is. So just as a reminder, parentheses equals not included. So basically that's going to happen where your series diverges. And your bracket means included, and that's going to happen where your series converges. So far we know that we can represent a function as an infinite series, and we're looking at these power series. And in the power series you have x raised to a power. So we want to find the domain of this function, which is the interval of convergence of the power series. Well, three things can happen. We only converge at our center, we converge everywhere, or we converge for a set of numbers, which then we'll have to check the endpoints to see if they're included or excluded. But how do we determine where we converge? How do we determine if we are option 1, 2, or 3? Well, we will use the ratio test to determine the interval of convergence. So recall, the ratio test was the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And we had three things happening with the ratio test. If the ratio test gave us a number that was greater than 1 or infinity, we diverged. So if you perform the ratio test on your power series and you get a number that's greater than 1 or you get infinity, you know that your series diverges, and that means that the interval of convergence for your power series is just its center, it's just C. Again, if you end up with a number that's greater than 1 after you perform the ratio test, or you get infinity, that means that your series has an interval of convergence at C at its center only. If you're looking at doing the ratio test and you end up with a number that's less than 1, we know that that meant that we converged absolutely. That means that your interval of convergence is going to be from negative infinity to positive infinity, because you can place any number in there for x and your series is going to converge. So if you have a power series, you're trying to find its interval of convergence, you do the ratio test and you get a number that's less than 1, then your interval of convergence is negative infinity to positive infinity. Our last option with the ratio test was if we were equal to 1. And we knew that with the ratio test, the way that we were looking at it before, then that was inconclusive. But now it changes for us. We won't be left with 1, we'll be left with the absolute value of x minus c. So if we do the ratio test on our power series and we end up with the absolute value of x minus c, we have to solve the inequality, the absolute value of x minus c less than 1, and then our interval of convergence is going to be from c minus r to c plus r, where again we're going to need to check the endpoints. So we have three options. We're going to converge just at our center, we're going to converge for all x, or we're going to converge from c minus r to c plus r. And we're going to use the ratio test to determine that. If the ratio test gives us a number that is greater than 1 or that's infinity, our interval of convergence is just the center. If the ratio test gives us a number that's less than 1, our interval of convergence is negative infinity to positive infinity. And if the ratio test leaves us with the absolute value of x minus c, we solve this inequality, we figure out what we're trapped between, we check our endpoints, and that's how we find the interval of convergence. Now before we start looking at problems where we find the interval of convergence, let's just make sure we understand how to find the center of a power series. Recall that we said in general a power series was the sum from n equals 0 to infinity of a sub n times x minus c to the n, and here is where you are going to be centered at x equals c. So how do I determine the center of the power series? Well, you look at your x value. So if I look at this first one, I just have an x. I have to set whatever that x is, or whatever's with that x, equal to 0 and solve for x. I am already solved for x, therefore I know that I'm going to be centered at 0. What about my next one? Well, I have an x minus 4 to the n. So I set that x minus 4 equal to 0. I solve for x, and I get x equal 4. That means that I'm going to be centered at 4. Our last one, I set 3x minus 2 equal to 0, and I solve for x. Here, I end up with x is equal to 2/3. That means I'm going to be centered at 2/3. So you're always centered at whatever value is with x. If there's no number with x, then you know that you're centered at 0. If there's a number in that parentheses with x, or numbers, like in example 3, set that expression equal to 0, solve for x, and that's where you're centered at. Let's look at the next 4 examples where we're trying to find the interval of convergence of the power series. It reminds us to make sure that we include a check for convergence at the endpoints of the interval. And then it tells us if your answer is an interval, enter it in interval notation. And if it's a finite set of values, enter your answer as a comma-separated list of values. And those are, again, just the directions you're going to see in WebAssign so that you know that you're really entering things in interval notation. Let's go ahead and start with number 4. I'm going to ask us every single time we do this where we're centered at, so we get used to seeing that, and then we can then relate it to whatever we get for the interval of convergence, so it can help make us understand what we're doing. For the first one, if I want to know where I'm centered at, I go to the x, it's all by itself, I set it equal to 0, so I know here that I'm centered at 0. Again, the problem is not asking us to determine where we're centered, we're just doing it for practice. The next thing I want to do is find that interval of convergence. Well, how do I find the interval of convergence? I use the ratio test. So recall the ratio test is that limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So let's set it up. The limit as n goes to infinity of the absolute value of a sub n plus 1. So instead of the n's, I write n plus 1. X, again instead of the n I write n plus 1 over 2 to the n plus 1 times n plus 1 factorial. And then I divide it by a sub n, but instead of dividing it by a sub n, I'm going to go ahead and multiply by the reciprocal. So the reciprocal here is going to be 2 to the n times n factorial all over n squared times x to the n. So now let's expand where we can, cancel, and see what we get. If we expand, well, n plus 1 squared, I'm going to stick that with n squared over here. X to the n plus 1, I'm going to write it as x to the n times x to the first, and I'm going to stick it over in x to the n. 2 to the n, I'm going to place that over 2 to the n plus 1, which is 2 to the n times 2 to the first. And finally, between n factorial and n plus 1 factorial, I know the bigger one is n plus 1 factorial. That's the one I'm going to expand. And that becomes n plus 1 times n factorial. Now let's cancel. My x to the n's will cancel. My 2 to the n's will cancel. My n factorials will cancel. And one more thing will cancel. I have an n plus 1 squared here and an n plus 1 in the denominator there. So 1 will cancel from the numerator and the whole thing goes away from the denominator. So let's see what's left over. I have the limit as n goes to infinity of the absolute value of just n plus 1 all over n squared times x over 2. Now let's find the limit as n goes to infinity of n plus 1 over n squared times x over 2. Well, the first thing is that we're taking the limit as n goes to infinity, so the only thing I can consider are things with n's. Everything else is just a constant multiplier, so these things here are just constant multipliers. So I need to find out, okay, when n goes to infinity, what happens to n plus 1 over n squared? Well, since that's an infinity over infinity, but it's a rational function, I know that I can just really look at those leading terms and reduce. So we're looking at the limit as n goes to infinity of the absolute value, and n over n squared reduces to a 1 over n, and that's still times x over 2. Well, what is that going to be? Well, the limit as n goes to infinity of 1 over infinity, that's just going to be 0. So this is going to be 0 times the absolute value of x over 2, but 0 times anything is going to equal 0, therefore we end up with 0. Well, 0 is a number that is less than 1, and if you go back to our 3 options from above, that puts us at number 2. Because if you end up with a number that's less than 1, you know that your ratio test told you that you converged absolutely. So what does that mean for us? That means that the interval of convergence, and I'm going to abbreviate interval of convergence as IOC. So our interval of convergence is going to be from negative infinity to positive infinity, because it doesn't matter what x values we stick in here. This thing is going to converge no matter what number we place in there for x. So if you think about it again on a number line, if this is 0, what I just told you is that I don't care what number you put in for x. You can put any number in under the sun. This power series will always converge.